Well, good morning, good afternoon, good evening, happy Thursday. Welcome to everyone to the webinar on the future of high-performance computing in wind energy. I'm glad you could join us today from wherever you might be. My name is Paul Viers. I'm the Chief Engineer at NREL for the National Wind Technology Center, and I've been asked to introduce our topic today. I'd like to ask everyone, since we're using an ordinary Teams meeting, to please mute yourselves, turn off your cameras. We're counting on all of our participants to help us avoid distractions in this meeting. So I would just like to say that the topic of high performance computing comes up because as engineers, we're always operating within the bounds of what we know, and we use margins in our designs to allow for what we don't know. Standard engineering practice works pretty well to the extent that we make systems that are both functional and survive. The practice has been used in wind energy to produce systems that are now durable, cost-effective, and being installed in gigawatts around the world. However, these buffers that we create to allow for unknowns really limit our ability to make innovations and make it impossible to really optimize the technology. There's a lot more that can be done, but there's a problem. The scale of tomorrow's wind turbines is pushing 200 meters in diameter. The machines often extend beyond the Earth's atmospheric surface layer. The complexity of the atmosphere, in combination with these range of scales, makes it somewhat problematic to uncover the unknown phenomena through direct measurement in the field. So many of our knowns are remaining hidden. Well, to take the next steps, we're going to need to integrate high-fidelity, full physics computational results into the way we solve for critical unknowns. These results also provide a means to increase the accuracy of the design and optimization tools, the ordinary engineering tools that we use to optimize these systems. Scientific discovery through physics-resolved computational models is going to be a major player in how we move forward across the industry. So Mike and his team are going to fill us in on how we're using the growth in HPC capability, as high-performance computing capability, to resolve the grand challenges of wind energy science. So let me turn it over to Mike Sprague and allow him to introduce himself. Mike?
Hey, good morning or good afternoon, everybody. Paul, thank you much for that introduction. Let's see, Alex, we can go back. There we go. All right. I'm having a little bit of trouble with my internet provider this morning. Let's hope this goes okay. I think everyone can identify with those challenges these days. So yeah, my name is Mike Sprague. The title of our talk today is The Future of High Performance Computing for Wind Energy. Alex, if you could advance the next slide, I can introduce our team. So I'm a research scientist here at the National Renewable Energy Lab, and I'm the PI for two projects that we're going to be talking about today. The first one is the ExaWind project, and the other is the high-fidelity modeling project. So I'm going to spend my chunk of time talking about, well, really motivating our efforts around predictive high-fidelity modeling for wind energy. And I'm going to talk about several of our team efforts, and then give an overview of our open source software stack, which we call ExaWind. I'm going to be followed by Dr. Shreyas Ananthan. He's a senior research scientist in the Computational Science Center. He's also the chief software architect for our software stack. He's going to talk about next generation high performance computing. He's going to try and talk about next generation computing, or really today's computing, where graphical processing units are used to accelerate computation. He'll be followed by Dr. Ganesh Vijay-Kumar. He's a research engineer here at NREL. He'll be talking about validation of our software stack, really showing or demonstrating the abilities to predict reality. And Tony Martinez, Dr. Tony Martinez, also a research engineer here at NREL, will talk about the very important aspect of how do we take these results from our high performance computing and high fidelity modeling and actually impact the way, impact the models that are used in the actual design and optimization of turbines. Alex, you can go next slide. Yeah, so to motivate our work, I'm just going to throw out this first bullet, and hopefully we're on the same page there, that more wind energy at low cost is a good thing. When we think about high penetration of wind energy, we're looking at large wind farms composed of large megawatt scale turbines, and that's both land-based and offshore. I like this image on the right because it shows well the scales that we're dealing with. When you think about the wind farm flow dynamics and the coupled turbine structural dynamics, you're looking at an extremely complex system that spans many scales. Depending on the quantities of interest you're after, you could have to resolve many scales of interest. So for example, if you're going to try to resolve going from the blade boundary layer at the turbine level to the wind farm level and possibly up to the wind farm level, you could have 8 orders of magnitude that you're going to have to resolve. Of course, that all depends on the quantities of interest you're after. I need to acknowledge that this image here is from a recent paper with the title Grand Challenges in the Science of Wind Energy that was led by Paul Beers. But a founding motivation here is that only when we can really model well a system can we optimize that system. Next slide, Alex, please. This image on the left, it's a little pixelated there, but I like this one because I think it shows what we're trying to do here, that the modeling and the computing can help us find pathways to reducing the cost of wind energy. So for example, can we predict and can we understand the formation of the wakes at the turbine, the propagation of the wakes and evolution of the wakes in a turbulent atmospheric environment? And then how do those wakes impact downstream turbines and how do they interact with downstream wakes? The image on the right, I brought this up here to point out that in 2015, for one of the advanced scientific computing research workshops, we highlighted predictive wind farm simulation as one of the computing grand challenges that is an excellent candidate for next generation exascale class supercomputers. Next slide. There we go. I want to step aside and make sure we can speak the same language here when we talk about modeling and computing and try to ground the audience in what we're talking about. Many of you are very familiar with this. But when we talk about high fidelity modeling, I want to focus on that model part. We're looking at a mathematical model, a description of a system using mathematical concepts. Really, an equation or a bunch of equations. For wind farms and high fidelity modeling, we're very much trying to adhere to first principles, and we try to make our simulations predictive. That is, we want to have as few tuning knobs as possible. We want to basically put in what we know about the system and get an answer about how that system is going to perform. When we talk about first principles, we think of things as conservation of mass and energy, Newton's second law of motion. We spend much of our effort on simulating fluid motions in the wind farm. And an accepted model for those fluid motions are called the Navier-Stokes equations. Again, we have a lot of wind folks here and people are familiar with these. These are the only equations I think we're showing today. And I put them up there just to illustrate some of the complexity we're dealing with. These are defined in a continuum. There's just a few equations here, but they're nonlinear partial differential equations. They govern fluid velocity, pressure, and temperature. If you can solve these, we're pretty confident that the solution of these equations will represent reality well. Next slide, please. So the question then is, can we actually solve those Navier-Stokes equations for wind energy systems? The problem here is that simple analytical solutions to those equations only exist for the most simple of problems and problems without turbulence. As soon as you bring turbulence in, you bring in orders more complexity. And that's because even though you might be interested in some of the larger scale dynamics, if you're going to capture those well, you need to capture all the subscales as well. And that's because of what is known as the cascade of turbulent energy from the large scales to the small. So for the wind energy system, it's extremely not simple and it's highly turbulent. So the only way that we're going to be able to solve Navier-Stokes for our problems is we do need to still introduce some number of approximations. We want to minimize that number. But for example, we do have to model turbulence at a certain level at least, and we do have to discretize the equations, which means we have to introduce numerical approximations. But basically, we take those few equations in a continuum and we convert them to millions or many billions of equations, which then we need computers. And for our billions of equations, we need supercomputers to solve those equations. And for those who do this, you would know that this can be a very difficult thing to do, to get solid solutions that you're confident in. Next slide, please. So our efforts are focused on what we call the ExaWind software stack. This is an open source set of codes. We have 3 physics-based codes that are in turn built on open source libraries. This is a multi-fidelity simulation and modeling environment. Okay, so you can run this code on your laptop, and that may be reasonable if you're looking at a fairly simple problem. But as your problems grow in complexity and cost, you can use the same stack to solve on any number of the supercomputers, and in the years to come on supercomputers or next generation exascale supercomputers. I'll briefly talk about the 3 software or physics-based systems here. The first is NREL. It's an unstructured grid finite volume code. We solve the incompressible flow, computational fluid dynamics problem. That we use to discretize the fluid in the vicinity of the turbine. That in turn is coupled to a structured grid background solver. That solver we call AMR-Wind. It's built on the AMRX libraries. That's also incompressible flow. We use overset meshes to couple these 2 different code bases. The third physics-based solver is OpenFast, which has been around for many years. That's our whole turbine simulation code. I put a link here that you can go to a 2019 NOEA paper if you want to see more of these. And all the GitHub links are there, should you want to get these codes or look at what's going on. Next slide, please. Our modeling approach was defined in 2015. We had a meeting of experts. We had 2 meetings, actually. The report is there. But that's where we decided to go with our incompressible flow model, where we decided geometry resolving meshes were required. We needed fluid structure interaction. We needed hybrid RANS LES modeling. And we needed nonlinear structural dynamics. Next slide, please. An important aspect of what we're doing and where many of our efforts are directed is to making sure that our codes have performance portability. It is really central to our development. And a big part of that is that supercomputers are evolving rapidly. The US Department of Energy, the supercomputers there, are increasingly relying on graphical processing units or GPUs for computational speed at low power. Shreyas will be talking about this in more detail. And we're really looking towards the first exascale supercomputers, which are going to come online in 2021. And those are going to definitely be CPU, GPU-based supercomputers. This is important not just for those who want to run on these fastest supercomputers out there. You're going to see GPUs becoming more and more common amongst clusters as well as other architectures. But if you have a CFD code that runs well on CPUs with traditional MPI communication, you really are going to have to think about what it's going to take to run that on a GPU-based system. I put an image there on the right of the Summit system. That's a 200 petaflops machine. That's today. And that one, as you can see from the note there about the nodes, while each node has 2 CPUs, it also has 6 NVIDIA GPUs. Also note that that's a 10 megawatt system. The first exascale systems are going to be at least 5 times faster, but they're only going to use, well, the goal is to have them use no more than 3 times the power. Next slide, please. Before we get to Shreyas, I want to make a couple of acknowledgments. The development of the ExaWind software stack is funded by 2 DOE offices. The first is the Wind Energy Technologies Office. That's the high-fidelity modeling project. The second is the Exascale Computing Project. Both of these are running from 2016 to 2023, and they both are a partnership between National Renewable Energy Lab, Sandia National Laboratories, Oak Ridge National Lab, UT Austin, and also Parallel Geometric Corporation, I believe. Next slide, please. We have a huge team here. And while there's just a few of us talking about the project today, This is really a rather massive effort with over 40 researchers at the 5 institutions. I want to call it specifically Paul Crozier, my co-PI at Sandia. He's the co-PI for both projects. But we have a lot of people here working all different aspects of the code base, going from visualization to linear solvers, overset grids, discretization, and so forth. Next slide, please. Next up, Shreyas Ananthan is going to talk about next generation high performance computing. I'm right up at my time limit. So Shreyas, I'm going to hand it right over to you. Oh, and everyone, just a reminder, if you have questions, please put them in the chat window, and I will moderate a Q&A when we're done with our hour here. Thanks. Shreyas, please take it.
Thank you, Mike. And hello, everyone. I'm Shreyas Ananthan. So I would like to start with a brief overview of the DOE supercomputers that are online today, as well as the ones that are coming online in the next couple of years that Mike just mentioned a couple of slides ago. So the idea here is to try and look at what makes them so powerful and what are the design choices that they use that might make it different from the laptops you use every day. Try to balance the power, computing power, and the energy consumption. So most of you here are probably familiar with Peregrine and Eagle, the flagship supercomputers that are at NREL. Peregrine was retired about a year ago, and Eagle is our current workhorse for all our wind energy simulations. So the Eagle machine is an 8 petaflop machine. And what does that mean? It means that it can perform 8 times 10 power 15 calculations per second. And that means you can put 8 and 15 zeros after that. That's how many equations it can solve in 1 second. That's really fast. But Alex, can you advance? If you look at some of the other computers that are available in the DOE leadership computing facilities, they are much faster than Eagle, and they occupy several of the top positions in the top 500 list. Eagle is 51st in the list, and if you look at the machine that Mike just talked about, Summit, that's second in the top 500 list. It's a 200 petaflop machine. That means it's about 20 times faster than Eagle and consumes about 10 megawatts of power. Just to give you an idea of how big Summit is, the room that holds all the hardware and the racks is about 2 tennis courts big, and it uses 185 miles of fiber optic cable to connect all these nodes together to have really fast networking to communicate between the nodes. And it has enough storage to hold 74 years worth of high definition video. But can you advance, please, Alex? So when we go further and look into exascale systems that are coming online beginning the next year, we have 2 machines that I'm highlighting here. One is at Oak Ridge Frontier, which will be the successor to Summit. And then there is another machine called Aurora, which is going to come online at Argonne National Lab. These are all exaflop, which means 10 power 18. So 1 followed by 18 zeros. That's how much computing power it will have. And you can see that it's going to be about 200 times faster than Eagle. 100 times faster than Eagle. And this is where the future is. And this is where we want to run our big wind energy simulations. Alex, please advance. So as you saw in the previous slide, DOE HPC systems present an unprecedented opportunity for unlocking novel insights into wind farm physics. Advance, please. However, the current codes have not fully harnessed the power of all this available computing power. We have sort of only run at the Eagle level and haven't really done large simulations to understand complex physics at this DOE leadership computing facilities. And that's because the existing codes are not well suited to running on the state-of-the-art HPC system. Next slide, please. And we will look at the reason why it is difficult to run our wind energy codes on this system. So what I'm showing you here is a sketch of what you would see inside a Summit compute node if you opened up the covers. So on the top, advance, please. On the top is the normal CPU and the RAM you would see in any normal laptop or workstation. And most of our codes are designed to run on these CPUs. But if you advance, if you look at where all the computing power lies, as Mike mentioned, they are all in these graphical processing units. And we really need to do a lot of work to move our codes from the top, where it's used to running on CPUs, down to the bottom, where all the computing power lies. Advance. And if you go further and look into the computer, the frontier that's coming online late 2021, early 2022, what is happening is that it's actually removing the CPUs and adding more and more GPUs, which means in Summit, you could run slower because there are enough CPUs. You could still run your codes, but it wouldn't run fast. Going into future, if you are on Frontier, you might not, your code might actually run slower than on Eagle, even though you are on a much powerful computer. Another thing that's happening is that Intel and AMD are also making their own GPUs, and it's not just NVIDIA GPUs anymore. So you have these different GPU architectures, and they require different levels of coding to make sure that your code can run as fast as possible on these machines. And it's not just about exascale computing. You can think I'm never going to run on exascale computers, but what is going to happen is that if NREL is going to replace Eagle in a couple of years, it is very likely that our NREL system that's coming online in the future is going to look a lot like Summit, and we need to be prepared for that. Next slide, please. But as Mike mentioned, another priority for our HPC code development process is that we just don't want to say that this code is only for running on exascale machines that you see on the top right corner. We also, as Mike mentioned, want to be able to make sure that this code runs on laptops and workstations that are available in the wind research community and in the industry. Not only do we want to run on individual workstations, but we also want to design the code and make sure that it can run on cloud computing so that industry can adopt this code and then use it for their own design and analysis and advance the state of wind energy. Next slide, please. So we have talked about all the systems and how they're complicated, and we are constantly asking the question, are we running to the best of our ability? Are we extracting the maximum performance out of these computers? So we need some kind of way to measure performance on the supercomputers. And the way we do that is using a metric called strong scaling. So the idea is quite simple. If I gave you 100 numbers and asked you to add them all up and give me the total, it will take you some amount of time. However, if you got your buddy to help you out, you could divvy up the numbers and add 50 each and then add them together to get the total. You might be able to do it twice as fast. So that is the same idea of strong scaling for computers. If you double the number of resources, that is adding twice the number of compute nodes, you are expecting to run twice as fast. Advance. However, the reality is that you are not always going to be twice as fast. You're going to be sometimes a little slower. And that's because just like if you had your buddy help you out, you both might add the 50 numbers at different rates. One of you might have to wait for the other person to finish so that you can add them up and then get the total. And eventually what happens is if you keep adding more and more resources, the cost of solving the equations on each node is eclipsed by the cost of keeping track of who is doing what and communicating between them. And so eventually you will flatten out and you don't see any more performance gain by adding more resources. Can you hit the next, please? So one of the main objectives for us within the ExaWind project is to close the gap. So we ideally want that orange line to lie right on top of the blue line, and we are constantly trying to push our codes to be able to do that. Next slide. So before I conclude my talk, I want to show you some examples of the kind of work we have been doing so far. So I'll take this example of an atmospheric boundary layer simulation and use that to show how we study the strong scaling performance of the code and how we try to improve it. So the atmospheric boundary layer simulation is just a flow in a box. We are trying to understand the complex flow as you see on the image here, where you have regions of high speed velocity on the top with the red colors and the regions of low speed velocity, which is the blue and green on the bottom. And the idea here is that we want to be able to solve this complex flow that would be that the wind turbines would experience. And the way we do this is by putting a lot of grid points, which are nothing but points in the flow field where we are actually going to solve the equations that Mike referred to. Next slide. So what I'm showing you here is the strong scaling performance of two of our ExaWind codes, the CFD codes that we use for analysis on the Eagle supercomputer that most of you are familiar with. The green line is the Nalu wind performance. So what we do is we start from a baseline, which in here is 5 Eagle compute nodes, and then we keep doubling that every time and see how fast can we run. The dotted black lines are the strong scaling linear performance. So ideally, we want both these lines to lie on top of that black line. As you can see, initially it's very close, but after that it starts trailing off and different codes behave slightly differently. And this is the part where we are constantly working on improving the performance. Another thing you will notice is that the two codes behave very differently. The AMR wind code, which is the red line, is almost 5 times faster than the green line. So why is that? So Nalu wind code is an unstructured code. And by that, we mean that it's a very general code with a lot of flexibility. You can use that code to model all the different parts of the wind turbine, whereas AMR wind code, as Mike mentioned in his intro slides, is a structured code. It makes a lot of assumptions which trades off the generality of Nalu wind in terms of speed. The good news is that for things like ABL simulation or just modeling the wind in a large domain which can span kilometers, that's what we need. So the idea is that in the ExaWind software suite, we have multiple tools in our toolbox which we can combine together to get the best physics at the fastest computational time. And that's our objective in trying to have multiple codes in our tool suite. Next slide, please. So what I showed you in the previous slide was just performance in traditional hardware. So the Eagle results you could probably replicate on your local clusters or your workstations today. So going forward, in this slide, what I'm trying to show is what happens if you go to GPUs, which is what's in the current systems like Summit and what's going to be there in the future systems like Frontier. So the orange line is the performance of the AMR wind code that you saw on the previous slide on the Summit CPUs. As you can see that because we've been working on these codes on CPUs for so long, they follow that strong linear scaling line pretty well. Whereas the GPU line is a little wobbly and it doesn't strong scale as far ahead as the CPU. But the good news is that when going to CPUs for the same amount of resources, that is, if you use one Summit node, GPUs are almost 10 times as fast. Or to think about it another way, if you fix your time to solution, let's say at 1 second, GPUs can solve a much bigger problem at the same time that the CPUs are capable of. And that's the good news here. Next slide. So now that I've talked about how we are optimizing our codes, I'll hand it over to Ganesh, who is going to talk about how we are validating these codes. Ganesh?
Thank you, Shreyas. Yes, so now I would like to talk about the building the confidence in our simulated reality. So the ExaWind project is focused on making scientific discoveries using predictive high-fidelity simulations of wind plants. And validation is key to establishing this predictivity of the wind energy simulations. So the image on the top left shows from the Grand Challenges science paper shows a modern wind plant today in complex terrain with wake interactions. The ExaWind framework solves the model equations on HPC platforms to predict the behavior of turbines and flow through this plant. The image on the top right shows another visualization of Q criterion and velocity contours of the NREL 5 megawatt turbine in uniform inflow. How can we trust the ExaWind framework results? So the validation exercise asks the question, are the equations we solve a true representation of the physics? And we answer this question through a systematic comparison to experimental data. This systematic validation exercise would also need to focus on all the aspects of aero-servo-elastic phenomena experienced by modern turbines as shown on the figure on the bottom right, including yard inflow for wind farm control, high shear and veer, atmospheric turbulence, floating platform motion in the case of offshore turbines, highly flexible bent twist coupled blades, and so on. So, next slide, please. Hence, a systematic validation exercise would need not just one, but a hierarchy of studies with increasing levels of complexity. The figure in the middle, borrowed again from the Grand Challenges paper, shows the different range of length scales affecting a turbine operation from the global weather effects down to the turbine scale. Representing these scales using a combination of different models in the ExaWind framework represents an increase in the complexity of simulations in the direction shown here. We have formed an international benchmark working group with people from the industry and universities to frame an appropriate hierarchy of benchmark cases that represents this increase in complexity. The images around the edges of this slide show a sample of the studies from this list, including a simple two-dimensional wall hump, an atmospheric boundary layer, a single turbine simulation in uniform inflow, all the way to a full-scale wind farm with multiple turbines. In the next several slides, I will show examples of the validation we have done as a part of this hierarchy and conclude with some of the work we are doing right now. Next slide, please.
Hey, Ganesh, we can't hear you. I think you might have been muted.
Hi. Can you hear me now?
Yes.
Yeah. Were you guys able to hear me the whole way? Okay.
We lost
Yes.
you for the last minute, Ganesh, I think.
Okay, so we show here two examples of the lowest level in the hierarchy of validation. A 2D NACA 0012 airfoil benchmark problem from the NASA Langley turbulence modeling resource and the McAlister-Takahashi fixed wing wind tunnel experiment. These sets of experiments are great to validate that our turbulence modeling approach is correct for the Reynolds numbers of interest. The images on the left show the aerodynamic performance of lift and drag coefficients computed using the ExaWind framework as a function of grid refinement compared to the benchmark solution from the NASA code. The image on the top right shows the mesh used to model the McAlister-Takahashi wing, along with the cylindrical mesh used to capture the tip vortex, an important part of the turbine-turbine interactions. The images on the bottom show a comparison of the predicted pressure profiles using the ExaWind framework along the wing compared to the experimental data in black dots, and similarly the velocity profile in the tip vortex. We are able to capture both the loads on the wing as well as the shape of the tip vortex behind the wing. Now this sets us up for to move on to the next phase of our hierarchy, more validation hierarchy. Next slide, please. This is the NREL Phase-VI wind tunnel full turbine experiment. So measurements were made on an extremely stiff 10 meter diameter two-bladed turbine with fixed RPM and pitch at the NASA Ames wind tunnel under extremely controlled conditions. So the images on we compare simulations of this turbine with experimental data from using the K omega SST RANS turbulence model. The image on the bottom left shows the meshes that we generated to model this turbine, including the overset hole cut. The image on the top right, in the middle top, shows the Q criterion and contours of velocity showing the wake behind the turbine in uniform inflow. The image on the top right shows the rotor torque, comparison of the rotor torque versus wind speed predicted by the Nalu wind simulation in blue and the experimental data in black with error bars. The results from other codes in the literature are also shown. We see that Nalu wind is able to capture the loads correctly at lower speeds, but that there is a lot more variability at higher speeds, similar to other codes that is possibly attributed to the transition model in the code. The images in the bottom right show the pressure profiles at a wind speed of 7 meters per second. And this shows that we can capture not only the overall integrated loads, but also the detailed forces along the blade that are important to wind turbine designers. So hence this experiment evaluation exercise shows that we can model a wind turbine operation and still capture the loads at lower speeds. But at higher speeds, there is a little more work to do. Next slide, please. Now we move along the validation hierarchy to model a megawatt scale turbine in the field. This exercise is a part of the IEA Task 29, focused on the Dan-Aero 2 megawatt turbine field experiment on the NM 80 meter rotor. So this rotor is 80 meters in diameter. So it's a significant step up from the previous validation exercise. The field measurements are performed on this 3-bladed turbine with full RPM and pitch control. So we are a part of an international group focused on the validation against the same experiment, and also a code-to-code comparison between all the participants in this group. As a part of this effort, we also had a greater collaboration with Denmark Technical University by using very similar grids, algorithm, and turbulence model. So the figure on the bottom left shows the overset measures that are used for this work. As a part of this exercise, we performed a validation exercise that is to be presented at the TARC conference in October later this year. So next slide, please. Next. Yeah, so the images on the top right show the comparison of the pressure profiles predicted by this by the NALU simulation in blue dots compared against both the experimental data from Dan-Aero in red dots, as well as the prediction from the ellipsis 3D from Denmark Technical University in the green lines. So this shows that we can capture the loads, load profiles along the blade of the turbine. The images on the bottom right show the total normal force profiles as well as the tangential force profiles compared to the Dan-Aero experimental data shown in red with error bars. So this suggests that we are able to actually completely model the relevant physics in a megawatt scale turbine in the field and validate well against that. Next slide, please. So now we move on to simulate the even bigger NREL 5 megawatt turbine that is an offshore-relevant demonstration. So this is the reference turbine established by NREL in 2009. This is a 3-bladed upwind turbine, again with full RPM and pitch control. So we don't have any validation data for this turbine, so hence we compare to other codes in the literature by performing, again, a RANS simulation with the K-omega-SST RANS turbulence model. The images in the bottom left show meshes that we, including the overset hole cut that we use to simulate this particular turbine under uniform inflow conditions. The images on the bottom right show the comparison of the power and thrust computed by the ExaWind framework against other codes in the literature, including another code, OpenFast, that is part of the ExaWind framework that is simply based on a lower fidelity blade element momentum theory. So we see that we compare the power and we predict the power and thrust well compared to the other codes in the literature. However, we kind of slightly under predict the thrust in the region of interest, which is the place where the power continues to increase between 5 and about 11 meters per second. So this was also a useful validation, a demonstration exercise to show that we can simulate not only just one turbine, but also 2 turbines as shown by the Q criterion and the contours of velocity on the top right. So this sets us up nicely to make sure that we can actually simulate the full wind farm simulations in the future. Next slide, please. So this, I conclude with some images of some results from current work that is ongoing to take us to the next level of predictive wind plant simulations. So this involves 2 separate topics. One is fluid structure interaction, as well as bridging the length scales using hybrid RANS-LES turbines modeling. So for fluid structure interaction, we have to consider not only just a rigid turbine, but also the movements of the blade and the deformations of the blade as the turbine is operating under any inflow conditions. So for this purpose, we have coupled the Nalu-Wind CFD solver along with the Aero Servo Elastic simulator OpenFast, where we transfer loads from the CFD solver to OpenFast and the deflections in the mesh velocity back from OpenFast to the Nalu-Wind CFD solver. The images on the bottom left show the comparison of the generator power and rotor thrust predicted by this coupled fluid structure interaction framework, and that was presented at a conference earlier last year against other code predictions. This shows that we are able to account for the under prediction of thrust in the region 2 of operation. The image on the right, we show the work involved in creating blade resolved simulations of wind turbines in atmospheric boundary layer turbulent inflow. The images show contours of velocity and wake behind the turbine through an ongoing validation with the IEA through the IEA Task 29. The rest of this work is expected to be completed later this year, and the focus of this work is to develop a hybrid trans-LES turbulence model that integrates all the length scales from the atmospheric boundary layer scale down to the boundary layer scale on the turbine blades. Next slide, please. So, in conclusion, the ExaWind framework is built on a strong validation base with increasing levels of complexity, all the way from an airfoil through fixed wing, single turbine and uniform inflow, all the way to a single turbine in the atmospheric boundary layer with FSL. Our goal is to be able to simulate a wind farm with flexible turbines in the atmospheric boundary layer with complex terrain or offshore in a completely predictive manner. That concludes my presentation. Thank you. I'll now transfer it over to Tony Martinez, who will talk about the HPC and HFM as a foundation for next generation engineering models. Tony?
Okay, thanks, Ganesh. Can you guys hear me okay?
Sure can, Tony.
Okay, thank you. So this last part of the presentation, I want to make a connection, and the connection is how can we use these high fidelity modeling tools to improve the lower fidelity models? And I'll show a couple of examples and the possibilities of the different things we can do. So I'll start saying what is the challenge? And the challenge is how can we use these models to design better engineering models? And I show a picture on the left of a large eddy simulation of a wind farm. This is a little ground wind farm. And there's a lot of level of detail in the simulation. So you're solving the fluid equations and you're getting this time history and all this information. And what we want to do is we want to be able to run simulations like what we have on the right. So that's a low fidelity simulation. It takes about a second on a supercomputer. But then when you run something like that, you lose a lot of information of the flow that you get from the high fidelity modeling simulation. So I want to show a couple of examples of how we do this, what we have done in the past, and what we can do with these tools. So next slide, please. So there's a spectrum of modeling fidelity. We have the higher fidelity modeling, which is a lot of what we do in this project. And the idea is that we solve the equations of motion with less tuning. And that is very expensive computationally, but it allows us to understand complex dynamics and look into physics of the flow. And then on the other end of the spectrum, we have the lower fidelity, which they're less predictive in a sense because they need more tuning to be able to work properly. But their advantage is that they're computationally cheap. But of course, the savings in computational expense comes by sacrificing a lot of the details of the flow that we can get from the more expensive high fidelity simulations. And then the lower fidelity tools we can use in things like optimization studies. So next slide, please, Alex. So I like to show the way I think about modeling fidelity is the following. So most of what we do is based on conservation laws. And Newton's second law is conservation of momentum. So it's force equals mass times acceleration. That's the F equals ma equation that you see there. And when we write it for a fluid, I said the Navier-Stokes, the momentum equation is that equation that we see in the bottom, and it's just in essence, it's just Newtonian physics. It's saying force equals mass times acceleration. Now, when I think about different levels of fidelity, I like to think of we're solving an equation like this, but we're making assumptions. We're making a lot of assumptions. So when we make zero assumptions, or the least amount of assumptions, we get to a solution of the flow that looks like what's on the right. And this is an image of turbulence. And the thing here is that you get a lot of details about the flow when you make zero approximation. This is the highest level of fidelity, and it's the most expensive computationally, but you get your full solution with all the details of the flow that you can have. Now, on the middle is what I like to think of as the mid-fidelity, where you make some assumptions and then you start losing some of the fidelity in your solution. So you can see how you lose a lot of the nice little features of the turbulence in that middle figure. And this is also expensive computationally, but it's not as expensive as the highest level of fidelity. And then on the left is the least expensive option, which just shows a lot of approximations. So basically, that's just a plot of the mean of that velocity field. And you can see that you've lost all the details of your flow. But the advantage is that you have a very inexpensive solution that you can run this on a laptop in a second. And I'm going to show some examples of these different levels of fidelity and how we use the high fidelity modeling to improve the lower fidelity models and create these very computationally inexpensive models. So next slide, please. So here's a sketch of computational cost versus model fidelity. And I give some examples of some of the tools that we use at NREL. So we have on our lowest fidelity, we have what are steady state models or steady state wake models, and Flores is a great example. This is one of our main tools doing optimization, like layout optimization. We use it for designing wind power plant controls. And that's the cheapest version. That takes about a second on a laptop to run simulations, or a couple seconds. And now we move up to a higher fidelity, and we have models like dynamics, wake models like FastFarm, that they solve a more complicated system of equations that includes dynamics. It changes in time. And you get a nice solution. And then the highest level of fidelity we achieve when we run the type of simulations like large eddy simulations and Blake Russell simulations. Now, those simulations require a lot of computational power. So I've put a picture down there of the Eagle supercomputer. And the idea here is that we want to use what we see on the right, so the highest level of fidelity, to improve those tools that we use on the left that can run very fast. So next slide, please. So what I like to do now is give a couple of examples of how we've used high fidelity simulations to come up and improve engineering models. And the first example is the curled wake. And Alex, can you please press go one slide so that the video starts playing? Oh, great, thanks. So here I'm showing a visualization of wind turbines in yaw and its flow field. And what happens when you yaw a wind turbine is that's just changing the angle. So wind turbines is really typically perpendicular to the wind, but when you change the angle, you generate this wake, and the wake is the turbulent structure behind the turbine. And what happens when you yaw, the wake moves, and that's what that video at the top is showing. So the wake is moving to the sides such that the wind turbine behind can see more wind. So the wake is redirected and it can produce more power. And what happened, like maybe 5 years ago, a lot of us started looking at wake steering using high fidelity simulations. And we started observing that as you do this wake steering, when you yaw the turbine, you can suddenly start producing more power from the second turbine. And the overall power that you produce is more. So we start trying to understand the mechanisms behind this, like why is this happening? So we start running high fidelity simulations. And on the left is some images from brainstorming that I had with Matt Scherf a long time ago, we started seeing, oh, look at this new shape that we're generating. Well, what is happening? Why is the wake so different? And that's when we started thinking about the curled wake and how can we model it? So can we go to the next slide, please? And what we did, we used the high fidelity modeling to understand the physics behind wake steering and the curled wake, and we came up with a simple model. And on the left is a diagram of how we did the simple model. So you have all these vortices, this circulating regions near the rotor, and they travel downstream. And then they generate that plane that you see behind that has these vectors. Those vectors are responsible for pushing the wake to the sides. And on the top right is some images of large eddy simulations. So these are the high fidelity simulations that we used to come up with a simplified model. And in the bottom, there are some results for this curled wake model that we came up with. And what I want to show here is that we were able to come up with a model from high fidelity simulation that produces a very similar wake profile, and it has all these mechanisms to generate the curled wake. And the nice thing is that this curled wake model takes about a second to run, as compared to the many hours in a supercomputer for the LES. And this model has been a great hit, and it's being used a lot in the community, and it's a big part of the work for the controls group here at NREL. And we're now still working on it and try to make it even faster for even more engineering applications, like optimizations. So the next example I want to give is flow over a wing. So Ganesh discussed some of these, and we have this experiment of flow over a fixed wing, and we look at the tip vortex. And when we do high fidelity modeling, there's different tools that we use, and one of them is the actuator line model. And the actuator line model is it's used to model the blade, and it can typically generate structures like the tip vortex of a wing. So what we did, we compared the actuator line to the blade resolve simulations. And on the left, you see this volume rendering of the velocity field. And you can see that long structure at the tip of the blade, that's a tip vortex. And that line there, we sampled the velocity along that line for the different methods, and that's that plot that you see on the right. And what we see is that the blade resolve simulations match quite well the experiments, and like as Ganesh had shown previously, they do a really good job of matching the reality. But now we notice that the actual line model did not do that well, and that's that red line that you see. So right now, we're doing some more work to improve the actual line model based on what we've observed from the blade resolve simulations. We're going to incorporate some of those findings into the actual line. So next slide, please. Now this example, this is a paper from Ganesh, Shreyas, and Shashank, where they start using machine learning. And this is a very new topic, and the main thing is that they use experimental data to train a machine learning model, and or a neural network to come up with a new simplified model for unsteady aerodynamics. And those plots that you see on the right for lift and moment coefficient as angle of attack, they show how well this new machine learning model, which is the blue line, matches the gray line, which is the experiment. And this has opened a new pathway for us where we can use high fidelity modeling to train the neural network and come up with better and more accurate, simplified engineering models. So next slide, please. And the last example I want to give is about this current work. So some time ago, Jason Junkman and Kelsey Shaler, they used this tool called FastFarm. It's a mid-fidelity tool, and they noticed that they were having some difficulties modeling wind turbines under high thrust coefficients. And that high thrust coefficients means that the turbine is producing a lot of force against the wind. And they they were having these issues because the models couldn't capture the right behavior. And we talked, and they said, can we use a high-fidelity modeling to understand what's happening with these high-thrust simulations? So can we simulate these conditions? And then how can we improve the models using these high-fidelity simulations? So we start running simulations using the ExaWind framework, and we notice something very interesting. And these visualizations show on the left, this is how a standard wake looks like. So when you have a standard thrust coefficient, so typical design conditions, you have these streamlines that pass through the turbine, they keep expanding. But what we noticed that was really interesting is that when you have high thrust conditions, and it's that plot on the right, that the wake behaves very differently. You see these streamlines, they go through the rotor, they expand a lot, and then they contract. And what this causes is, like, the wakes that are generated under high thrust conditions are very different. So we're right now working on this, and we're coming up with a new model so that we can simulate these high thrust wind turbine wakes with a much cheaper computational cost. So I think this is a great example of how we are using right now these tools to improve the lower order model. So next slide, please. So I'd like to summarize by saying that I always think of like, what would the pioneers of wind energy have to say about these high fidelity modeling? And the main thing is that I like to point out that the way I think of it, the best minds and the new generation can only go so far without the right tools. And I think of high fidelity modeling as this essential tool that will help the next generation of scientists to develop the new methods and the new tools and models that will be used in the industry to build the next generation of wind turbines and control algorithms. And with that, I'd like to finalize this part of the talk, and I'll hand it over to Mike Sprague for some final thoughts and a Q&A.
Thanks, Tony, and thanks, Ganesh and Shreyas. We're right on time. I think that's pretty impressive. Yeah, so I have a few questions here from the audience. I'm going to go into those. On this Q&A slide, though, I just want to point out the next frontier for what we're doing within the High Fidelity Modeling Project. Many of you know there's increasing interest in moving offshore, and that's the next frontier for our ExaWind software stack. And I put one of our recent images that Yorgos Deskos put together. He's working within the Nalu wind solver right now and enabling atmospheric boundary layer simulations in an offshore environment. So that's a wind wave interaction simulation there. I want to move to some questions right now. Shreyas answered one of them a bit, but I think, Shreyas, I'm going to give this one to you again, though. And I think Keith asked it right in the beginning there. For a lot of people, what's the big deal here? What's the huge difference? What's the fundamental difference between GPUs and CPUs? And maybe you could speak to the interaction between the two on these next generation systems.
Shreyas, you're muted.
You're still muted, Shreyas. Oh boy.
Why don't we go on to the next question, and he can work on his audio.
Yep. Shreyas, maybe you can get your mute fixed while we go to the next question. Next question, Tony, this one's for you. The question was, will the concurrent precursor inflow method be included in the new code? Can you explain what that means and then answer that question?
Sure. So if I understand correctly, there's the concurrent precursor method. That's when you run your precursor simulation at the same time as you run your wind plant simulations. And that's done a lot of times in pseudospectral codes. But in the codes that we use, we typically don't do that. And the main reason for that is that we like to store the boundary inflow data and use it on different simulations. So in the concurrent precursor simulation, you have to run both simulations at the same time every time. But with the method that we use, where you run a precursor, you can run a precursor once and then run many simulations using that same boundary data. So hopefully that answered the question.
Thanks, Tony. I'll give this one to Ganesh. In the code, the lower part of the AVL will be modeled with RANs or with wall model, or both features will be there. Ganesh, you want to comment on that?
Yeah, thanks, Mike. So thank you for the question. The specific modeling strategy will depend on the exact simulation being performed. In most cases, with ABL, the lower part of the ABL will still be modeled using a wall model. The exception would be in some cases where we are doing a blade result simulation where we have the turbine as well, in which case we are working currently on developing a hybrid RANS-LES turbulence model that works across the entire range. In that case, we might consider moving to a RANS approach at the lower surface of the ABL, near the lower surface of the ABL. But for most part, right now, we are using a wall model for the ABL. I hope that answers your question.
Thanks, Ganesh. I think Shreyas might be back and able to speak. Shreyas, are you with us?
Can you guys hear me then?
Yes, we can. I think I muted you and you couldn't get unmuted. Sorry about that, but go ahead.
That's okay. Thanks, Mike. So yeah, to answer Keith's question, so one question he asked was, why are GPUs fast? Are they taking shortcuts? So initially, GPUs were used for graphic processing. That's why the name GPUs. But nowadays, they are general purpose graphical processing units. So they have come a long way from their old roots where you had to really run single precision to get the speedups. The graphic cards that are the GPUs that are on Summit, the runs that I showed and the speedups that I showed were actually using the same double precision computations as you would do on the CPUs. To go further and elaborate on what Mike asked about what is the difference between CPUs and GPUs. So CPUs are designed to be general purpose, right? So they are not only meant to solve equations really quickly, but also handle networking, handle the user interface, putting stuff on the monitor, handling the keyboard interactions, writing stuff on and off the disk. It's supposed to be general purpose. So it can do mathematical calculations, but it has maybe, you can think of it as 2 or 3 lanes on an interstate. Whereas GPUs they trade off that thing and they say, we will focus on mathematical computation. So instead of having like 4 lanes on interstate, GPUs give you 128 lanes. So you can pass a lot of cars. But the thing is, they can't do all this other stuff. They are not suited for writing stuff onto the disk or interacting with you. So if you type something on the keyboard, the GPUs never see that. They are designed for one task and one task only, and that's to run computations really fast. So we are never going to get rid of CPUs. We still need them, and when we start our program, they still run on the CPUs. The trick is to identify which parts of the code have a lot of calculations, like adding up thousands of numbers or billions of numbers, and ship that calculation over to the GPU, whereas the CPU performs other coordinating tasks. And this is where all the programming and the strategies come in. And how do you do that by shipping stuff off and getting the stuff back? How do you manage that, all that interaction? That's where all the coding complexities lie. I hope that answered your question, Keith.
Yes, thank you very much. That's perfect.
Thanks, Shreyas. Let's see, the next one has to do with cloud computing. I'll read it. You mentioned the support of cloud platforms, which could help industry to more quickly take advantage of the software stack. Any progress, demos, pilot projects on that front? So I'll take that one. We're very much focused on the big systems that we talked about already in this talk. The challenge with the kind of simulations that we do here is that we need this very well-connected system. So in a sense, we can do the computing in the cloud, but we need dedicated, next to each other, well-connected HPC type cloud computing. So not a lot going on there within our projects, but certainly other projects at NREL, it's of great interest. So hopefully that answers that question. This next one, Shreyas, I'm going to give you this one again, and maybe you want to talk about the NYSERDA project. Would mesoscale phenomena, such as low-level jets, be considered in the model framework as well? High computation power could be helpful.
Yes, yeah. So the project that we talked about today is high-fidelity modeling, and we focused a lot on the codes that we are developing for doing wind farm simulations. But there are other aspects of wind energy funded activities that are happening in at NREL and other labs that are looking at what is called mesoscale microscale coupling. And Matt Churchfield is one of our researchers at the NREL lab who's leading that activity here. And we are looking at exactly that. How do we bring in mesoscale phenomena that is predicted by mesoscale codes? How do we put that into the microscale code and run all this together? Another activity that is happening is through NYSERDA funding, we have another activity in collaboration with GE, where we are looking at low-level jets and their impact on offshore energy production, as well as the fatigue loads and the lifetime of the turbine. So there are multiple activities going on, both using the existing code base that we are developing, but also other codes that are looking into coupling mesoscale phenomena with microscale phenomena.
Thanks, Shreyas. Let's see, the next question is about data. How are you going to handle the huge amounts of data coming from these future simulations? Are you considering open platforms for sharing simulation setups and results? So that's, I'd say, a work in progress. One of the big projects within the Wind Energy Technologies Office is the DAP, or the Data Archive Portal. And we've often talked about trying to get our important benchmark simulations onto the DAP. That hasn't happened yet, but certainly, well, and the other aspect I'll mention is what Ganesh mentioned, which is the benchmark working group, where we're trying to establish our validation cases. And so it is my hope that we will get all of those, or at least the most important data sets, out there in the public. Let's see, the next question. Will there be any opportunities for PhD graduate students in developing the code? So as I mentioned, all the codes that we're talking about today are open source. So in the sense of, is there an opportunity to develop? There certainly is. Anyone can come in and make what is called a pull request if you or introduce, or if you find bugs in the code or you want to request new capabilities, you can do so on GitHub. And if you have a new capability you want to implement, you can always introduce that as a pull request. And you should have seen the links to GitHub for all the codes in the presentation. I believe we will be making this presentation available to everyone. I just got another question. I'm reading it right now. Alex, while I'm reading this, do you want to comment on the availability of the presentation when we're done?
Yes, we're going to be posting it online. The presentation materials will be posted online, and we'll send an email to the group letting you know where you can locate it, and then it most likely will be also available through the Teams link.
Thanks, Alex. So the next question is about multi-rotor technology. So I'll read it. Multi-rotor technology is still in its infant stage. DTU has presented initial results from this project with 4 rotors on single tower. Have you run any pilot projects for multi-rotor systems to see how wakes work here? Again, we do not know if multi-rotor systems come into commercial stage or not, but certainly interested to see how wakes work here. Thanks for that question. It's so the quick answer is no, we haven't run any multi-rotor systems in the sense of what DTU has done, but it's a great example of I'll give it somewhat outside the box thinking on a technology innovation. And the framework, the simulation, modeling and simulation framework that we're establishing here is just perfect for something like that. There is no reason that we can't do such simulations with the ExaWind software stack. So, right, the idea would be we'd do the simulation, we'd be able to look at performance and make some judgments about its viability, hopefully, and understand what's going on. I don't know, does someone else on the team want to add anything to that? Shreyas, Ganesh, or Tony?
Yeah, I just want to add that, so the code base is generic enough and it's intended to be an open source platform to do such technology exploration, right? So the point is a great point that, these are the kind of innovative technologies that we probably don't currently have the tools today, but if we had a high fidelity modeling capability, which is solving fundamental equations from first principles, that is the platform on which you can test out all these concepts and do that. And that's certainly the hope.
Thanks, Shreyas. Let's see, I think I got all of our questions addressed that were put in the chat window. If you have another question, get it in there now. Otherwise, I want to thank the team again for speaking today. I want to thank all of you for taking the time to listen to us this morning. Hopefully we found it interesting. Oh, we got another question here. Are there any experimental efforts currently going on at NREL to provide validation data sets for these new tools? Oh, short answer is yes, but I'm going to pass that off to Ganesh. He might want to elaborate on that a bit.
Yeah, thanks, Mike. We are working on setting up the next phase of experiments for several turbines in the field. Some at NREL, some not at NREL. We do have a few turbines through commercial agreements set up already on site, and so from which we have collected data. So we are trying to do validation against some of those data sets already that already exist. And we are also involved heavily in setting up the next phase of experiments, which will give us a lot more data for the validation. So this is again a part of the International Benchmark Working Group as well, and collaboration with a lot of other different projects going on at NREL, including the Wake Dynamics project and a few other projects.
Our colleague, Mike Robinson, what is the greatest experimental validation need at this point? Well, from my perspective, Mike, we need to start with in our validation hierarchy is that megawatt scale turbine and with flexible blades, with well-characterized inflow and well-characterized outflow so that we can understand beyond just the turbine itself, but the nature and of the wake formation and evolution. Does you guys want to add anything to that? We've got one more minute here before our time is out. So
high Reynolds number, flow characterization at really high Reynolds number to understand hybrid trans turbulence modeling, that would be another, I mean, it is in the, somehow tied into all the stuff you said, Mike, but I would specifically like to call that out.
That's great. Thanks, Shreyas. Well, Alex, it looks like we're right at our time limit. Anything you'd like to say as we close up here?
Thank you, everybody, for attending. Look out for the materials, the presentation materials to be posted on the team site as well as online. And we appreciate your commitment to attending today.
Thank you much, everybody. Have a great rest of your day or evening, depending on where you are.
Thank you. Bye.
Thank you, Mike.
Thank you.
Thank you.
Thank you. Bye.